Today we have our ultimate tool in avoiding doing limits. This is section 5.3, and it's the fundamental theorem of calculus. So we started off with limits, and those were great and fun, and then we got derivatives. And we spent a whole bunch of time trying to avoid doing limits for those. Now we have integrals, and those are even worse. And so now we actually have a way to avoid doing limits for those. And the fundamental theorem of calculus comes in two parts. The first part is what I identify as being the fundamental theorem of calculus. And the second part is something I like to call the evaluation theorem because it helps us to evaluate our integrals. It's basically the time-saving measure we have from section 5.2 where we define the definite integral. But we had to take this limit and break it all apart and stuff, which was okay for polynomials, but it's not so much fun if I wanted to find, for example, the integral of sine of x from 0 to pi over 2, because I don't have any sum properties that would help me evaluate that. So if f is a continuous function on a closed interval from a to b, then g of x, defined by the integral from a to x of f of t dt, and here what we mean by this is the integral from a to x is a function defined for x, where x is in a to b. So if x was equal to a, then this would have a value of 0, but if x was equal to b, then it would have the value of the full integral from a to b of f of t dt. Well, that function is continuous and differentiable on the closed interval, maybe not on the endpoints. But in particular what we have is that the derivative of this integral is equal to the inside function. And what we take away from that is that the integral from a to x of f of t dt is an antiderivative of f of x. So in particular we have a shorthand notation for the antiderivative involving the integral, and we'll say simply that the integral without bounds of f of x dx is equal to whatever antiderivative I find plus c. Now the second part of the fundamental theorem of calculus is a really useful one that helps us to evaluate our integrals. So from the first part, since the integral is essentially the same thing as an antiderivative, that means I actually have a very easy way of evaluating my integrals. So let's consider this. If f is continuous on a to b, then the integral from a to b of f of x dx would be equal to big F of b minus big F of a, where the big F is some antiderivative of little f. And we can think about how this works out. If the integral from a to x of f of t dt is an antiderivative, so this is equal to some antiderivative plus c. I might not know what the c is, but that's okay. Then the integral from a to b of f of t dt is equal to big F of b plus c. And here I'm just replacing the b's from the x's, but also using the same silly technique actually. The integral from a to a of f of t dt, this is equal to big F of a plus c. And here I'm replacing the a's in place of the x's. But I also know that this is supposed to be equal to 0. In particular, this says that c is equal to negative f of a, whatever that is, big F. Which I put back up here, and I get big F of b minus big F of a. Which is a nice, cute little justification of what we had there. Which means for all those integrals where I, wasted a bunch of time doing Riemann sums, I could have just found their antiderivatives and plugged in a couple of numbers. So if we remember our first example, when we had the integral of 4 minus x squared from negative 2 to 2, we got 10 2/3. And I did a whole bunch of work to get that. Or I could have just done the antiderivative. The antiderivative of 4 minus x squared is 4x minus x cubed divided by 3. But what I want to plug into that is negative 2 and 2. So I had this extra bar here saying that I'm going to plug in these bounds for this integral. And I do the top bound first, and followed by the second bound, and I take their difference. So this is going to be 4 times 2 minus 2 cubed over 3 minus, we'll add some parentheses, because everybody likes parentheses, 4 times negative 2 minus negative 2 cubed over 3. And when I simplify all this, I get 8 minus 8 thirds minus a negative 8 minus a negative 8 thirds. So many negatives. We have 8 minus 8 thirds plus 8 minus 8 thirds, which is 16 minus 16 thirds, which, as I recall, is the same thing we got at the end of all that work with the Riemann sums and the limit. So this is 48 over 3 minus 16 over 3, which is 32 over 3, which is the same thing as 10 plus 2 thirds. Huge time saver. But the evaluation theorem actually gives us a very nice way to solve fundamental theorem of calculus problems. It actually gives us a much more general way to do them too. So if I wanted, for example, to say that some function is equal to the integral of, let's say something I don't know, the natural log of x. No, I should not use x's all over the place. I use t's down here because I want to use x's in the bounds. The letters inside the integral don't really matter so much as long as they match, but it can get very confusing if the variable for your integral matches the variable in the bounds. And we wanted to avoid any possible confusion, so we try to make them different. So if I wanted to find s prime of x, for whatever reason, say, we don't necessarily know what this antiderivative is. I don't know what gives me a derivative of natural log, but I might still need to maximize this function for some reason. And so I'd need to take a derivative. Well then, s prime of x, according to the fundamental theorem, is going to be the natural log of x. And I just kind of ignore the 3. But there's a reason for that. So the derivative of s of x would be the derivative of the integral from 3 to x of the natural log of t dt. But according to the evaluation theorem, this integral in here is equal to some antiderivative, but I don't know what it is, so I'm just going to call it big F of x minus big F of 3. And I'll say that big F prime of x is equal to the natural log of x. I don't really know what it is. It turns out I won't need to know what it is, because when I apply this derivative here, I'm going to have the derivative of this antiderivative minus the derivative of this antiderivative, this time evaluated at 3. So here I have big F prime of x minus, when I plug a number into a function, I get a number back, and the derivative of just a number is 0, so that's why we get to ignore the constant lower bound. But since big F prime is equal to natural log, that means this is just the natural log of x. Doing this process allows me to do problems which are not immediately covered by the fundamental theorem of calculus. For example, if s of x was equal to the integral from 2x to 7 of the natural log of x, of t dt, the statement of the fundamental theorem of calculus is from a constant lower bound to x in the upper bound. But I have a constant upper bound, and I actually have 2x instead of just x in the lower bound. The fundamental theorem of calculus doesn't tell me what I'm supposed to do when I have more than just x in here, but I would be able to flip the bounds on this by multiplying it by -1 and then applying the fundamental theorem to that. However, since the fundamental theorem doesn't cover functions inside the bounds of the integral, I should use the evaluation theorem to deal with this derivative. So when I apply the evaluation theorem to the integral, the antiderivative of the natural log, which is heretofore unknown, big F of 7 minus big F of 2x. And when I apply the derivative of f of 7, that's 0, minus the derivative of f of 2x. And here's where our favorite derivative rule comes into play. I have to do a chain rule because I have a function inside of a function. So I have big F prime of 2x multiplied by the derivative of 2x, which is just 2, meaning I have the natural log of 2x times 2. So when I have different functions as bounds in my integrals, and I need to take the derivative for whatever reason, I have to deal with the chain rule. So I could have a very complicated example where I have g of t this time is the integral from sine of t up to t squared plus t plus 2 of the arctangent of x squared minus x with respect to x. This looks like a pretty awful setup, but we actually deal with these kinds of integrals in calculus 3 when we take calculus up to the third dimension. So if I wanted to find g prime of t, the fundamental theorem of calculus says I should just plug in the bounds in place of the x's and rewrite my function, but I also have to multiply by the chain rule. So g prime of t should be equal to the derivative. If I jump a couple of steps, I'll say big F prime of x is equal to arctangent of x squared minus x. So here I should have big F of t squared plus t plus 2 minus the lower bound, big F of sine of t. And when I apply the derivative, I'll have big F prime of t squared plus t plus 2 times the derivative 2t plus 1 minus big F prime of sine of t times cosine of t from chain rule. But remember, the x's, whatever is I'm plugging in everywhere where there's an x. So I actually have arctangent of t squared plus t plus 2 quantity squared minus t squared plus t plus 2 times 2t plus 1 from chain rule minus arctangent of sine of t squared minus sine of t times a cosine of t. Jumping into 5.4, which I've already leaked into a little bit because 5.4 technically contains the indefinite integrals I wrote before, but an immediate result from the fundamental theorem of calculus is the net change theorem. So since the integral is an antiderivative of your function, that means the integral of a derivative should involve the original function. So if I have the integral of a rate of change across some interval, then the result is the net change in values of the original function. So, for example, if I had a velocity, the velocity is the rate of change of position. So let's say I had a velocity of negative 3t plus 40, and I wanted to find the total displacement of an object between two times. It won't tell me exactly the position because I don't right now I don't have knowledge about where my object started, but I do know the velocities. So I want to find the displacement of this object on a 10-second interval starting at 5. We'll say this is in seconds, just so we have units, meters per second. Then displacement is a net change in position, or how its position has changed from a prior position. So I would find the integral from 5 to 15 of v of t dt, and this should give me the position at 15 minus the position at 5. But this antiderivative is negative 3t squared divided by 2 plus 40t, and that's evaluated from 5 to 15. So I have negative 3 times 15 squared over 2 plus 40 times 15 minus, add some parentheses, negative 3 times 5 squared over 2 plus 40 times 5. So what does this number look like? 15 squared is 225. So I have negative 675 over 2 plus 600 minus negative 75 over 2 plus 200, which is minus 675 over 2 plus 600 plus 75 over 2 minus 200, which, if I'm not mistaken, is minus 600 over 2 plus 600 minus 200, so that's 400. So this is equal to minus 300 plus 400, 100 meters in some positive direction. But recall that displacement is not the same as total distance traveled. If I wanted the total distance traveled, I would have to take the integral of an absolute value. And the reason for this is somewhere during this interval, my velocity is negative, so I'm going backwards. And then somewhere along this interval, my velocity is positive, so I'm going forwards. And though that travel time is kind of canceled out, because for some portion, my integral is giving me a negative area, and that's canceling with the rest of the integral, where it's giving me a positive area. So the easiest way to do this is to decide where the velocity is positive and negative. So we'll set it equal to 0, and we'll get 40 equals 3t, or t is equal to 40 divided by 3. Now, I have a fairly simple function, so I can tell right off the bat that before this time, my velocity is going to be positive, and after this time, my velocity is going to be negative. And I know that because this is a linear function and my slope is negative. So I know that my velocity is going to look something like that. So when I do the absolute value thing, I should do the integral from 5 until 40 divided by 3 of regular v of t, because it's positive there. Plus, I have to take care of the rest of the integral, and I could do two things. I could either say the integral from 40 over 3 to 15 times negative, or of negative v of t dt. Since my velocity is negative after this point, when I take the absolute value, that's the same thing as multiplying by negative 1, forcing it to be positive. Since I'm going to have a negative here anyway, the other thing I could do is kind of trick the bounds and have an integral from 15 to 40 over 3. These are going to give me the same value because the second version, the bounds are flipped. And that's the same thing as the negative of the forward version that I have above. And so I would evaluate this limit to find the total distance traveled as opposed to the displacement across that time interval. This encompasses the topics of 5.3 and 5.4. 5.4 includes a table of antiderivatives, again, because the indefinite integral, the integral without bounds, is the shorthand notation for finding the antiderivative of a function. But this list is the same as the list we would have had for antiderivatives, which is reading reference page 5 backwards, but also can be found on reference page 6 under the basic forms in our table of integrals. So in particular, the ones we want to know on reference page 6 are numbers 2 through 15. Number 1 on that list is integration by parts, which is a calculus 2 topic. We learned that fairly early on. And the ones after 15 are a good idea to know, but those particular forms are the result of U substitution, which is the next section, which is after this first test. So we would want to know numbers 16 through 18 when A is equal to 1 in particular. That's all we're going to require for this test.